So I just want to briefly mention center of gravity. If g has the same value at all points on the body, its center of gravity is identical to its center of mass. So in almost every case, we can just call center of gravity equal to the center of mass. The only time center of gravity can't be approximated to be equal to center of mass is in situations with very tall things like skyscrapers, which is this drawing is attempting to be. So as an example, the acceleration due to gravity at the bottom of this ginormous skyscraper thing, these two towers, which look like kind of corn cobs sticking out of the earth there. The acceleration due to gravity at the bottom of these things, this is a 452 meter tall thing. They're called the Petronas Towers in Malaysia. It's only 0.014% greater than at the top. So whatever it is here, it's only 0.014% greater than what it is all the way at the top. The center of gravity of the tower is only about 2 centimeters below the center of mass. So on an object of this scale, the center of mass only differs from the center of gravity by about 2 centimeters. So this is why we're not going to talk too much about center of gravity or calculating center of gravity. It just, if you're building a skyscraper, you want to know that there is a difference. But for all our purposes, there's pretty much no difference. But there are a few interesting things we can say about center of gravity before we move on. For one, the lower the center of gravity, the harder it is to tip something over. And you probably have heard this in terms of, sports or trucks carrying loads on highways and such. So your center of gravity must fall vertically within your area of support to not fall over. So let me get rid of all this, and I'm going to draw something out here. So if you have a car, let's see, this box is going to be a car with its tires here, and it's on some curved or sloped road, right? And it's heading, let's say, away from you. Its support is from here, I'll do it in red or green, is from here to here, right? The width of its tires. And so if its center of gravity is here, then vertically that does fall within the support there. But if we were to have it be on a steeper slope, like here, it's on this steep of a slope, well then that's no longer vertical. Get rid of these dots. And its center of gravity is being pulled vertically down like this, and that is outside of the range of the support. So this thing tips over if it's just sitting there stationary. So that's interesting. That goes for your own stance of your body and everything else, right? Another interesting thing that we can talk about is ways to find center of gravity. And as you know, it's pretty much the same as the center of mass. So there are simple tricks that can be used to find it. If you have some weirdly shaped object, it doesn't have to be too weird, just anything that isn't completely symmetrical so you're not sure. So let's just say this mug here. Right, you want to know the center of gravity of this mug. Well, you could do all these calculations. You can say, oh, this bit we can use as this, and it's this far away from that, and you can say, well, this is pretty much a cylinder, and you can do it mathematically, and you can find the exact answer. But there's a couple of easy ways to do it. And one of them is if you hang this thing by a string, if you're able to do this, if you're able to attach a string to it. If you hang it from a string, it will hang so that the continuation of this line from the string that it's hanging by crosses somewhere where its center of mass is, which isn't exactly there, but it might be somewhere close. So that gives you one axis. So the center of mass definitely exists on this line. Then you take it and you rotate it and you hang it by another string. So then you hang it here maybe. And then you have the center of mass existing on this line. And so the center of mass exists on the intersection, because the first line was like this, right? Second line is like that. And so the center of mass exists at the intersection of those two lines. And so if you're able to hang it by a string and draw some lines, or at least just kind of like put something in place to hold, then you can figure it out sort of. An even easier way would be if we took this mug here, and there's a joke that goes along this that I heard in a physics class. I guess it's not really a joke, it's just something that physics majors like to hold things over other majors, and so this one's between physics and math, and it goes that you're in an interview, and it's between you and the other guy, and we'll say you're the physicist and the other guy is the mathematician, and you're asked to find the center of mass of this mug, and so mathematician immediately starts taking measurements and going to work on figuring out the center of mass mathematically, doing integrals and approximating to various shapes that fall within it. Well, you, the physicist, you take it to the edge of the desk here. You can see it is the edge of the desk. This is the surface. And you just slide this bad boy right over to the edge. And you just keep inching it along right until it starts to tip. And right where it starts to tip, that gives you the plane that the center of mass exists on. And so it would be somewhere right along there. And then you just take it and you rotate it and you do the same thing, similar to the string method. And then you see where it begins to tip a different way. And the intersection is the center of mass. So some people can tell that very well, and it's entertaining. But either way, that's about all I have to talk about with center of gravity, because it's pretty much the same as center of mass. I guess before we move on, we can talk about the oddities of center of mass a little bit. So center of mass is odd when it doesn't exist within the volume of the thing. So we talked about a donut before, and how the center of mass doesn't fall within the volume of the donut, and that's the same thing for this mug here and other things as well. And that's kind of weird, right? So you have some donut thing. I don't know how to draw it. Well, you have some donut thing, and the center of mass is in the center, but it's not within the volume. So how does that make any sense? Well, really, I think it's best to just think of any system as being just a collection of large particles, right? And what the center of mass is, it's kind of like a physical representation of an average. It's a mass-weighted average, right? So in the same way that if I asked a room of 100 people what their heights are, and then took the average of everybody's height, it's very possible that the average height belongs to no one, right? So maybe the average height of a room of 100 people is 5'6". There might be nobody that's 5'6", but the average can still be 5'6", and that's the exact same way that the average mass, right? The mass-weighted average of this distribution of mass here can exist where there isn't any representative to exist. It's just the average, right? So that's one way to think of it. And gravity will act the same way on all of these particles. So if you just imagine all of the bits and crumbs of the donut, right? Let's just say it's broken up into a billion little particles, and they're each able to move independently. And if I let this thing drop, and we're not talking about air resistance and it's in a vacuum, and let's say you're even ignoring the collision between the particles, right? They're each just going to drop straight down. It's not that they are attracted to the center of mass, right? As it falls, they're not all going to be attracted towards the center of mass. They're all going to be dropping straight down because each of them is just a particle of mass, and gravity is acting straight down on each of them. The only reason that that we have the center of mass here is because we're considering all of them, and they are all part of this big system, which we are calling a donut. But that's just kind of like a construct of our language and our experience in the universe. So we know this to be a donut, and so we attribute this whole thing to be a system. But really, it's just like a huge collection of individual particles, and each individual particle is just going straight down. But together, to us, it makes up a donut, and we're considering that the system. Hopefully that clears that up a little bit. It's a really interesting topic, center of mass and center of gravity. And it's hard to get your brain around at first, but I think maybe the height average thing might help clear the conundrum up a little bit in people's minds. But all right, so that was a little blurb about that. We kind of go back to equilibrium. We just stuck this in here to revisit it. All right, see you next video.